Georg, and thank you also for the invitation to talk at this. It's a really great privilege to be on your One World series. So I guess I don't really need to introduce myself. I can't do better than that. I'll just say that today I'll be talking a little bit about clustering of extremes in climate. So when we talk about clustering of extremes in weather or climate, some things that pop in my mind are things like flooding events, where we see these several consecutive days of heavy rainfall that cause massive flooding in areas. For example, the picture on the left here is a picture of Hurricane Harvey, which is something that I was personally in. And that's actually what the streets look like pretty much everywhere, not just on one street. And on the right-hand side is actually a picture of the flood that happened recently in Brisbane in 2022 when I first moved here. And this is just a picture I took outside of my house. I also think about things like heat waves, for example, where we have these several days of consecutive high temperature values for maybe an average temperature that sits above some value for a long time. And this is actually a picture of what the heat wave looked like in 2019 when I first moved to Dresden. So I started asking questions like, can we address this idea of consecutive extremes from an extreme value stance? And of course, it's a natural framework to ask. So when I say things like extreme value theory, I think it's good to give some background and what that means. So if we have some sequence of random variables, x1 through xn, then we define our maxima in our system as the max from x1 to xn, and under IID conditions, we get something called an extreme value law. What I mean by IID is independent and identically distributed. And this extreme value law just tells us what the limiting distribution is of these maxima. And we say that that's e to the negative tau, where tau is some function of y, and we'll explore what that means in just a second, and actually the next slide. So if we choose our thresholds for building this limiting distribution of our maxima in a very specific way, we get something that's really familiar in all of these different statistical platforms. When we use extreme value theory, we get what's known as the generalized extreme value distribution. And this is thanks to Nadenko and Fisher and Tibet. And really, it just says that if we choose UN to be one parameter linear families that look like this for some AN and BN, then the limiting distribution takes one of three types. And those three types look something like this when we plot them in a PDF. So if we have some shape parameter that's positive, we get an upper bound, or I'm sorry, if negative, we get an upper bound. If we get a positive shape parameter, we get some polynomial decaying tail, which is a bit faster than exponential, which is what we're used to in the normal distribution. And then, of course, we get, for the shape parameter to be equal to 0, these exponential tails. Now, the problem with all of the framework that exists from, say, the 1950s is that it assumes this IID, or this independence on our sequence, and we don't have that in the real world. So the question came along, can we somehow extend this idea of an extreme value law and hence a limiting distribution for our maxima when weak dependence exists in our system? And thanks to Ledbetter, the work of Ledbetter and Chernick, we can. So if we have a sequence of constants, and again, we can choose them very similarly to what we saw before, this says that if we satisfy these two dependence conditions that were introduced by Ledbetter, called D and DK, then if the limit exists, the limit looks like this. So it's e to the negative theta tau. So the only difference between this limiting distribution and the one we saw before is the introduction of this new parameter called the extremal index, and that's that theta value. And the idea here is that 1 over theta represents roughly the average cluster size of our exceedances. I wrote a little bit about how we define the extremal index in different ways, but they're all related. So the first way that was introduced was by O'Brien in 1987, who looked at this limiting distribution that Ledbetter created or derived, and said that beta is just the parameter of the distribution, and used probability theory to work that out. Now that doesn't work well for people who are doing statistics, because we can't just employ that in a time series setting. So what Singh did in 1988 was considered the limiting distribution for the number of returns of the over some high thresholds. It's a little bit different than the magnitudes, the distribution of magnitudes, and found that this follows what we call a compound Poisson distribution. And the idea is that once you reach over threshold, you'll reach over threshold a few times, and then you'll go back down, and then happen again. And the first occurrence occurs with some Poisson, and the compound part is part of this extremal index, this clustering. So then I'll just skip down to the bottom here. Farrow and Seegers in 2003 actually worked out the maximum likelihood estimation of this extremal index in the compound Poisson, and that's the typical numerical value that we use to estimate this. And then it was just only Farrow that I wrote in 1991. Smith and Bison started looking at different ways of measuring the extremal index from a time series stance, but this is not a way that we use anymore. Now, when we're trying to estimate the limiting distribution of the maxima from
Meagan, can I ask a quick question? If you
yeah,
go
of course.
back one slide. Can you comment on why you're not using the over threshold cluster size from the time series, like the Smith and Weissman?
Yeah, of course. Well, when we found this isn't as accurate, but the reason is because you have, say, some fixed time series, and what they have to do is set some really high threshold. And what's the definition of really high? We don't know in this case. And then it's to the algorithm looks for the first over thresholds and then picks some kind of block size and says, okay, if you occur over threshold over the certain block size, then you're considered part of your cluster. And if you're not, then you're part of a different cluster. But the problem here is that we have to input all those values. We have to pick the block size. We have to pick the threshold. There's no natural way of setting up like a process in statistics that allows us to get around this. So it's really dependent on what you decide in the end.
Yep, thanks.
Yeah, of course. Thanks for your question. Whereas Farrow-Seegers, looks at the maximum likelihood estimate of a compound Poisson, so a limiting distribution, and that's the only assumption that you have to make on that. Okay, so from a nonlinear time series setting, we look at xn, which is like a sequence of measurements of some observable. So consider something like daily rainfall. Now, in order to be able to estimate the limiting distribution of maxima, we have to somehow define what a maxima is in the setting. And the idea behind this, it comes from this dependence condition D and D prime. So you have some long sequence, you block it up into pieces of length n, and you take the max over each piece. And what D prime does is across each piece, so between M1I and M2I, D prime guarantees decay of correlations between those maxima. Oh, sorry, D guarantees decay of correlations between those maxima, but D prime or decay guarantees decay of correlations within the block. So all it says is, decay says that you don't have too many recurrences of maxima inside a block. So from that argument in the probability theory stance, we build a statistical method upon which we can guarantee that M1I to MMI are somehow weakly dependent enough that we can guarantee a limiting distribution exists. And this goes all the way back to the work of Markov, and then Gumbel, and then Ledbetter, and finally to us. So for some fixed block length, we have some fixed AM and BM. So that BM plays the role of location, or you can think of it like a mean, and AM plays the role of like a variance in our sequence of thresholds, which means that if we can assume the limiting distribution is a GEV, which we can using this blocking for long enough blocks, then we just have to estimate the parameters of the generalized extreme value distribution, which are the mean, the scale, and the mean, the scale, and the shape parameter using some likelihood method. Now, the problem with this idea of blocking is that it removes all clustering by its very nature, because you're taking one value and then you're shoving it into a distribution. And so the best that we can hope for example, in the case of daily rainfall, is we can answer the question, what's the probability of observing a single yearly maximum of daily rainfall above some extreme threshold? So we can't say anything about runs of these extremes. Now, you could go back and say the extremal index tells us something about the cluster size, right? And we can get some kind of relationship between our generalized extreme value distribution and one that comes from a weakly dependent system, thanks to this theorem by Coles. But what this essentially is saying is that the generalized extreme value distribution for a weakly dependent system with an extremal index that's not equal to 1, that value gets buried into the location and scale parameter of our distribution. So we don't get any of that clustering information out when we're fitting a GEV. That's here and here. So some people have said, all right, let's look at the extremal index separate from the GEV. We can fit the GEV in the maxima and then somehow get an understanding of clustering by just considering the extremal index. And here I've actually used the Farrow-Seeker's estimate to estimate the cluster size of extreme daily rainfall across Australia, the eastern part. And you can see that we get some understanding of like spatially what's going on with these kinds of storms. So in the way that I see this is some big storm moves in from the north and it starts to break up as it moves inland and down. And that's that, like you have larger cluster size, more days of heavy rain in the north and along the coast than you do inland and in the south. The problem is that we still can't say something about the probability of returns of these consecutive extremes, so we don't get some exact estimate, which is what we really want. So a solution to this is to introduce some idea of a functional to preserve a consecutive property. The first that comes to mind is something like a time average, right? So over k days, the average value of rainfall or the average value of the temperature in that k day range. So that would be yi. So we could also consider the k windowed minimum functional, and that's the minimum value over k days. And the benefit to that windowed minimum functional is that if one value is above some extreme threshold, then of course it guarantees all k are above some extreme threshold. So we keep that consecutive property that we want. Now, the problem is that when we introduce these, they reduce the data to be able to fit the tail of the distribution. So that means that our accuracy goes down significantly as we increase k, this window size. So one question that we had was, can we somehow use theory to make statistical inferences that allow us to improve accuracy? And I know that seems like a general question, one that we all ask at all times. But from our perspective, what we want to do is pull this problem out, put it into the dynamical framework, see if we can solve something there, and then bring it back to time series. And that's what we're going to talk about. For this talk, I focus on the k windowed minimum functional only. But I will just say that not only do we have some results for the k windowed time average functional in the paper, but I've worked with Matt Nickel and Holger Kantz in 2020 on using things like importance sampling methods for this short time average. And then obviously Freddie Boucher, Ragone, and Wooters over at Reading have looked at these important sampling methods, but in the large deviations approach, and they've done some really nice job for these longer time averaged functionals. Okay, so now we have to talk about how we would do something like this in the dynamical framework. So what we consider is something like a space X, a map T, which is ergodic and measure preserving. So it's really nice. It has a probability measure. And then we introduce an observable into the space. And our observable typically takes the form of some function of the distance in the classical sense to a fixed point, so as Georg was asking me before. And we build some stochastic process on this. So as our X evolves under the map, so we get this orbit, our observable changes as well. And then the idea here is to prove some version of these dependence conditions that were originally introduced by Ledbetter, and they're called Cyrillic D and Cyrillic D prime, Cyrillic DQ, and they were originally introduced by Freitas, and Todd in 2010. We want to prove that they hold for our stochastic process. And then if we can prove that, our limiting distribution is exactly what's given by the extreme value law from Ledbetter. So as I mentioned a little bit, the classical observables for extreme value theory and the dynamical framework look like these. So I won't go too much into them, but the idea behind choosing each one of these is that they give each of the three types of distributions that we want for extremes. So a type 1, if we have a negative log of a distance, a type 2, if we have a distance to a negative alpha, and a type 3, which is our bounded value, if we have C minus some distance to a positive alpha. But of course, some value of a distance to some point of singularity doesn't really help us in the physical sense, so we can't really get any information out of that. So we did some work on looking at extreme value laws for more physically relevant observables, where we're not looking at a point of maximization, we're looking at a set of maximization, and that's this little curvy S here that I've written. But we still look at a similar function, so negative log of that, or the distance of this to a negative alpha. So we can still get those three types of distributions out, only now we've replaced our point with a set. And we have some proofs actually from 2019 that look at a coupled system of expanding maps, and no-soft maps, and the Sinai dispersing billiard model. Keller and Liberani did some nice work with the two-coupled system, and Speranda, Gowdy, Giraud, and Vienzi in 2018 also looked at coupled systems of expanding maps, but from a transfer operator approach, which is a really nice paper to read.
So can I ask a question again?
Yeah.
About this curly S, this set of maximization.
Yeah.
How do you have to, can you comment a bit about, like, is this something you choose, or is this like the attractor that's dynamically given, like a set, rather than looking at a fixed point, you look at a set now, like an attractor. Can you comment a bit on how I should view this set of maximization?
I have a drawing a little bit further down the line. And I was debating whether I should put it here or later on. But that's a great question. So we're looking at something that depends on how, like, the type of set you choose depends on the system that you're looking at. So for example, the ANOSOF system, a natural set there would be a line in the space. And then you would look at expansion away from the line, and you have this like expansion, contraction, and then you have the line that wraps sort of around, and it looks really fancy. And I'm happy to give a whole different talk on how that works. Similarly for the Sinai dispersing billiard model, because we can reduce that to a map that looks very similar to the ANOSOF system. And for the coupled system of expanding maps, we think of things like the invariant plane. And that's what I have a drawing of. So it really is just kind of exploiting these systems to build a set It's not like we take a set and go, that looks like energy, and then we try to solve that, because that would be very difficult to do.
Okay, thank you.
Well, actually, along those lines, Mark Holland worked with a few people well before this. I can't remember exactly the date, but I'm happy to send you the paper. Looking at physically relevant observables that take some crazy forms, but their intersection is just a point with the attractor. So then it looks like simply the distance to a fixed point, and then you can do your classical stuff. Yeah.
Okay, cool. Thanks.
Thank you.
So in the Anosov case, is your Anosov map linear? Is that why you choose a line? Or I don't really see why a line is sort of matching the Anosov system.
I mean, sorry, I don't understand your question.
Oh, well, maybe I misheard. I thought you were saying in the Anosov case, then you would choose the set S to be a line.
Yeah, we do choose it to be a line.
Is that just because it's easy or because it's somehow adapted to the system?
Yeah, because it's easy.
Okay.
Sure.
Okay.
Yeah. And it's really, so maybe I should point out that like the argument that we take is it's not a transfer operator argument. So it's a geometric argument. And we're looking at trying to take a neighborhood around our set. And then we're trying to estimate how often does that neighborhood return to itself. And it's quite simple to do that in the Anosov system with a rectangle, because you can just take the pieces on the edge of the rectangle to be 1 over n, and then trace those back and let them intersect.
Okay, but the rectangle doesn't have to be adapted to stable unstable manifolds or anything like that. It can be an arbitrary rectangle.
It can be. That's right.
All right.
It doesn't have to be. So there are like 4 cases. And some of them, they have to be aligned. Like we look at aligned with unstable, aligned with stable, and then neither.
Okay. All right. Thanks.
Thanks for your question. Yeah. Okay. Right. So getting back into it, this is sort of the meat of the talk here. So hopefully I'm doing okay on time. Yeah, I am. All right. We have this lemma from our recent paper in 2024, and this isn't taking into consideration these observables yet. This is just a lemma for some general sequence xn, and yn defined as either the average or the minimum functional. And the result of this comes from directly this work by Coles. So it says that if we have bn as the max from y1 to yn, and x is defined as before, so it can be some stochastic process. Mn is the max of the xn's. Then if we have a limiting distribution for the maxima for xn and a limiting distribution for yn, then we can choose our thresholds wn as some fancy function here, which depends on the window size and the map, and that as a product with the UNs that we discussed before. Then we have some relationship between all of the parameters. So I'd just like to point out here that this, to me, from a statistical point of view, is the most important aspect of this lemma, and that we get this max stability property that the shape parameter doesn't change, even if we change our maxima to maxima of the functional instead. And the reason why, to me, this looks the most important is because to fit the shape parameter, you need the most amount of data. It takes the longest time to converge. So to be able to say something about the shape means that we can actually fit the distribution on the maxima mn, where we haven't lost data, and then infer what the distribution will be for bn, or at least what the shape will be. So here's some motivating example, and it's a bit unfair because it's in the IID case, but this is just to show you how we would choose AN and BN, or why we chose the AN and BN that we chose for our proof. So if we have xn as a sequence of IID standard Frichet random variables, they have a limiting distribution that's Frichet, and we can choose an to be n to the 1 over alpha and bn to be 0 so that we can derive that limiting distribution. So that is here. And that's a Frichet type. So our outline for the proof of the lemma is to choose Bn to be 0 and An just to be some arbitrary An. We choose Un to be An times Y since Bn is 0. So this is just our one parameter linear family as before, and Wn as we required in our theorem. Then we have our two limiting distributions that look like this. And for some fixed large n, our maxima follow this distribution G. And this to the theta 1 allows us to invoke Cole's theorem. So we can rewrite our Bn in terms of G theta 1 as this. And like I said, as by Cole's consequence and max stability, we have this relationship pop up. Okay, great. So the outline of our approach here to be able to prove all of this stuff, so our limiting distributions and do some statistical inference, is to find an appropriate GKT for each system that we look at. That's what it comes down to. But in order to do that, we need to establish that there is, in fact, a limiting distribution for yi, and we do that by proving that the dependence conditions hold. And then we can estimate our retrieval indices using O'Brien's formula because we're in some probabilistic space, and then estimate our scalings. And some hyperbolic systems that we consider in the space are piecewise expanding maps, these unit interval, hyperbolic Taurel automorphisms, or NOSOF systems, and weakly coupled systems of expanding maps. So this is I know it looks a little bit messy here, but I'll just point out some of the key properties. The first is that we choose our observable, not just to be the distance between x and a fixed point. That's for the case of A, where we have an expanding map, just a single one, but also x to some set of singularity for our NOSOF system or for our coupled system of expanding maps. And if that's all chosen in this way, then we have the following relationship between our parameters. So we still, obviously, we get this max stability property, and then we get some relationship between our location and scale parameters. And the G of KT here is just derived as our lambda to the negative, and then this is the window size, K minus 1 alpha, where alpha is a shape. Okay, so I'll just go through a little bit the outline of the proof, which is that if we have some sequence of observations, so phi taken on iterations of the map, as we set up before, then we can define some events. So one event is remember we were just discussing if we have some singularity set, then we're looking at where we get really close to that set. So that's where our maxima occur, and that's what UN is. And then we want to make sure that when we leave UN, we don't come back for a certain amount of time. And if we do that, then we're done. We can prove that the extreme value law holds. And then again, we can invoke O'Brien's formula, thanks to Freitas, and Todd, which is just this ratio of the probability of leaving and then coming back and being within the set. Okay. Great, so we can think of T as in A, B, or C. So these are the three systems that we're considering. Our observable is taken so that we have a Frichet limiting distribution because our lemma is built for the Frechet distribution. And then we look at these k exceedance functionals. So yi is the minimum over k values, which means that, like I said, if one of them is above some value, all k of them are above that value. And then we can define Wn such that we have this required normalization, which I didn't point out very much in the extreme value law, but that's where it comes from. Okay, so we know right away that yi is maximized at points closest to p, or if we're looking at our invariant set, closest to our singularity set. So that means if the minimum of these is just the value of phi furthest away from t, but we know that t is some kind of expanding map, so it's going to be the value of t furthest away. So that's k to the k minus 1. And then we can estimate exactly how far we are away by this uniform repulsion by lambda. So what that means is that we are, in fact, our yi's are just scaled versions of our xn's. And because of that, we can immediately say that if the dependence conditions exist for our xn's, then they exist for our yn's too. And we've proven that these exist in 2021. And finally, we can work out exactly what the limiting distribution is by just choosing Wn to be un times this, this function that we worked out here. Okay, so I didn't actually mention this, but I very much enjoy doing things from a numerical perspective. So if there's any way that we can do numerics in a paper, I love to do that kind of stuff. So here's some results for the doubling map with our theorem that we just stated from 5.1. Oh, well, it's 5.1 in the paper, sorry. Just assuming that our observable is a Frechet. And we can see that the theorem fits quite nicely with the estimated, and this is maximum likelihood estimated scale and shape, or scale and location parameter. For those of you who want to know a little bit more about how we can trust results that come out of chaotic systems, Lou Carini and also Ferranda have done some really, really nice work in this area of numerics for chaotic systems, and it's summarized very nicely in the Extremes in Recurrence book in chapter 9. I also do this for the weakly coupled system of expanding maps. So this is our expected, the line is our expected scale from our theorem, and then the dot is, of course, maximum likelihood estimate for both of these. Now, one question I had was, these fit really, really well. So is there any way that we can get some numerical inference for this, where we're in the setting that phi is maximized at our invariant set? And the setup here is I did a really long run Monte Carlo simulation with really long blocks for the maxima. And I compared this to performance of a short run from maximum likelihood estimation and a short run invoking our theorem. And you can see that the blue is where we invoke the theorem, and the red is where we just do standard maximum likelihood estimation on our maxima. So actually, this works quite well for window sizes. So the window sizes I showed you here, I think were 5 and 6. And this works quite well for window sizes actually all the way up till 20, where we still get this empirical tail decay of the shape parameter that's expected. And I didn't tell you what that was, but it's 0.2. Now, the reason why our maximum likelihood estimation does such a bad job here is because we're reducing the tail data. So we can't actually fit anything. There's nothing to fit. And that makes MLE do a very poor job naturally because it needs to fit data where data is not available. And you can see how this happens when we increase the window size. So this is for k equals 10, this blue one, where you don't get very many estimates in a tail. It sort of makes sense because how often do you see 10 extremes in a row? Probably not very. And then the red is where we see the original distribution. So one question we had was, can we somehow now pull this out of the dynamical framework and put this into a real world application? And we started thinking about the two-coupled system of expanding maps and how this is just some kind of invariant set here. So we have a line, but really a line of singularity, but really around like a small neighborhood about that is where we observe these extremes. And then as we move away, the extremes become smaller and smaller, right? So we thought maybe a rainstorm sort of behaves like this. And I put a picture of rainfall over the Philippines in 2013 from NASA, which just if we focus in on, say, a square here, we can see that we have some center where we have maximum rainfall. And as we move out, rainfall decreases. And that was our mindset for just trying to see if we could use these methods in rainfall data. So here we grabbed 23 years of daily rainfall data over 60 stations. So the reason why we did this in Germany, there's two. The first is that the Deutsche Wetterdienst has an amazing amount of data. It's like, wow, so good. And the second is because the rainfalls, I say roughly stationary, and we can talk about that, what that means at the end if there are any questions, but it's just this idea that the fluctuations are so small that they don't really affect the numerics. And then we use maximum likely estimation for the shape, the scale, and the location over increasing windows of length k for this minimum functional. So what we're trying to do is see what's the probability of observing 2 days of heavy rainfall, 3 days of heavy rainfall, and so on as we increase k. Now, from our theorem, we expect something like this. There's a relationship between the location of each window size k and the original location value. And we can estimate this lambda parameter by just invoking the fact that it's, in theory, 1 minus theta. And we can use Farrow-Seegers to estimate this theta. And then alpha is some maximum likelihood estimate of the shape parameter. Now, if all of this is true, we should have something like a linear fit when we take a log here. So a log-log plot of just this relationship. And I'll just show you what this looked like in data. So in the red is our theorem. So what we would expect if everything was true and all the fits were perfect. And the blue is a regression estimate along the values that we get out from maximum likelihood estimation. So it's not perfect, but we tried to see if we can use this to fit the data. And this is what we get. So if we apply our theorem, the blue, is our theorem estimate, and then the red is the maximum likelihood estimate. So in this case, the answer is yes, we can use this to improve return level estimates for consecutive daily rainfall extremes. So the next question we had, of course, came down to, can we say something about heat waves? So we want to look at, instead of the Frichet distribution, which is well known to fit rainfall data, the Weibull distribution, which is this upper bounded tail distribution, often is used to fit temperature. We find that temperature fits that quite nicely. That's the type. And part of that reason, I think, is just because if temperature went on to infinity, we wouldn't be around. So there must be some implicit bound there. So here's our theorem from our paper. So if we're looking in the Weibull case, so that's just everything is the same, only now we've changed the observable to be the Weibull observable. And we get this relationship out between each of the parameters. So if we do this for the coupled system of expanding maps, this is what we get. So we've got our theorem estimate and then our estimated from maximum likelihood and maximum likelihood over a very long run. Just point that out. Now, the problem is that we couldn't really justify the use of invoking this distance to an invariant set. And when we actually did try to simply apply the theorem, it doesn't really work. So instead, we thought, let's just try to apply the lemma, the original lemma that we've derived, to see if we could get any inference for temperature data. And the way that we applied this is we said, okay, the lemma says that we should have some linear relationship if we take the log of gkt and then the log of the values that we get as an estimate of the variance and the extremal index, which we take from Farrow-Segers. And the idea is then to fit some kind of generalized linear model on this log of gkt and then use that model to predict the mean. And if it does a very good job, then there must be G of kt must have been estimated well. So that's this part here where G hat is our estimate from GLM. And this is what we get. I haven't fit the confidence intervals here because they're actually quite wide for this data. But the blue is just from doing a GLM and trying to estimate what the location would be. And then, of course, the red is maximum likelihood estimate. And I'll just say that the reason why I think this fits so much better than MLE is once again because we're invoking this idea of max stability. So we don't have to worry about fitting the shape to these significantly decreasing tail estimates. We can keep the shape the same and then do our best to estimate the location and scale, which converge faster. So here's a list of some other results we have for our paper. So we have some stuff for the minimum functional with the Frichet domain, maximized at a non-invariant set. And we also have some stuff for the average functional, as I mentioned before, and the Frichet and Weibull for invariant and non-invariant distance, a distance to not invariant, non-invariant set. And some further applications for this are obviously this idea of max stability. So we can start to look at how can we better estimate the location and scale, but keeping the shape the same and seeing if we can get any inference out of other things, not just rainfall, but anything that follows some kind of Frichet or Weibull distribution. So that's just directly applying a lemma, which doesn't require us to look at distance to an invariant set and that kind of thing. What's often very common is that we see this blind statistical fitting in engineering and climate papers. And the reason is because they often call platforms, and these statistical platforms do not take, obviously, any of this into consideration, this change in the shape parameter, because it wasn't known until now. Now, I'm currently working on a project that uses this property to estimate multi-day precipitation across Eastern Australia. And this is just an image that shows this max stability over window size. So it's not block size. The block size are the different colors, but this is of window size. And what we can do is say, we know that over increasing windows, the shape should not change. So we can pick an appropriate block size that allows us to choose our GEV model appropriately. So this is, say we wanted to estimate returns for 3 days. We know that our block size would need to be 1 year or greater to get this max stability that's expected. And then from these models that we've created, we've actually found a few things. So the first thing is that we see an increase in SOI contribution for increasing days of extreme rainfall. So what that means is even though the location, or sorry, the mean and the standard deviation are decaying as we increase the number of days we're looking at for extreme rainfall, the SOI factor increases. So it plays a bigger role in these longer days. We also find that we have an increase in the likelihood of observing consecutive extreme rainfall on the cities that are more inland. So we don't see much of an increase in probability of 1 day extremes, 2 day extremes, 3 day extremes over these coastal regions like Townsville, Brisbane, even Sydney. But for example, Karanji Farm was used as an inland station, and we see that the probability, say, observing 1 day is actually increased twice when we look at 3 day consecutive extremes. So really, that just means that when we're talking about ENSO and we're looking at El Nino and La Nina, we see that the El Nino period actually plays more of a role on inland stuff than it does around coastal regions. Okay, so here are some ongoing projects that we're looking at. So first, we're looking at optimal block lengths. So looking at convergence rates to these limiting distributions now that we've introduced functionals. We're also looking at results for the Gumbel domain. So as you might have noticed, we only have things for Frichet and Weibel right now. And we're also looking at whether or not we can create some very solid, reliable statistical tools invoking this max stability property. I'd just like to say thank you again to everyone for allowing me to give a talk at One World. And these are just some pictures of my collaborators that I mentioned before. So from the left is just Matt Nickel from the University of Houston, Mark Holland from Exeter, and Holger Kantz from Max Planck. And then I also mentioned Feng Tran, who's Matt's PhD student, who should be graduating quite soon, but I don't have a photo of her.